Now you might remember from earlier in this chapter that we could do a hydrogenation of benzene. It just takes extreme pressure. You see this is 100 times higher than atmospheric pressure, 150 degrees Celsius, and sure, we can hydrogenate it, and we release 208 kilojoules per mole for benzene, and we talked about the stabilization of benzene. However, it says alkenes can be selectively hydrogenated in the presence of a benzene ring. So sure, we can reduce just this vinyl group here using hydrogen, platinum, but now we're only using a low pressure. It's 2 atmospheres, and it's also at a low temperature. You can see that we release only 117 kilojoules per mole here, and you might be wondering, why is it less than a double bond, which is around 120? And the reason why is because this double bond is fully conjugated. Notice it goes double, single, double, single, double, single, double, single, and there's stabilization that comes with that. And you might remember that in Organic Chemistry 1, we saw that alkynes could be reduced via dissolving metal reduction, so sodium and liquid ammonia, and we use that to make a transalkene. But benzene can also be reduced under similar conditions to give us this compound that we call 1,4-cyclohexadiene. So this is 1,4-cyclohexadiene. Right? Why would we call it that? Look, 1, 2, 3, 4. So our first double bond starts on carbon number 1. Our second double bond starts on carbon number 4. So 1,4-cyclohexadiene, you can see clearly this is not an aromatic compound because this carbon and this carbon are now sp3 hybridized. So it's definitely not an aromatic compound. But let's take a look at the mechanism. And since we're using sodium, you might remember that the electron configuration of sodium is neon and then 3s1, like that. So that means that sodium only has 1 valence electron, and so the Lewis structure of sodium is just sodium dot, like that, 1 valence electron. And so you can see here that the sodium donates an electron, and when it does that, we end up with a radical anion, right? Why do we call it a radical anion? Because you get a radical and you also have an anion in the same intermediate. Then the methanol acts as a proton donor. Then we end up with a radical. So then what happens in the second step is we're going to donate another electron. And we see that right here. Our sodium donates another electron, and now we get an anion. And now the methanol donates another proton. And so we reduced at this carbon and this carbon, which are on opposite sides of the ring, to one another. And so things to note. Number 1, we call this the Birch Reduction. So this is what we call the Birch Reduction. So Birch, it's named after a guy named Arthur Birch, who was an Australian chemist. So sodium, methanol, and ammonia is our solvent, okay? And it doesn't completely reduce the aromatic ring, right? We end up with our 1,4-cyclohexadiene, and the sp3 hybridized carbons are on opposite ends of the ring. Now you might be wondering about regioselectivity. If I have a substituent on my ring, okay, let's say I have an R group on here, how is the reduction going to occur? Okay, what will it look like in that case? And there's 2 scenarios that we're going to look at in this class. The first one is if we have an electron donating alkyl side group. So we call that an electron donating group. And remember that alkyl groups are electron donating via hyperconjugation. And so if you have an alkyl group, okay, so let's imagine that this group here is alkyl, then that carbon that's attached to the alkyl group is not going to be reduced. Okay, it doesn't undergo reduction. And the reason why is the alkyl group is donating electron density, so you wouldn't want to put a radical or an anion there because that's going to destabilize the intermediate. And so the conclusion is, if we have an electron donating alkyl group, that carbon to which it is attached will not be reduced. Now, on the other hand, if we have an electron withdrawing group, so we'll call that an EWG, an electron withdrawing group, like this carbonyl here, right, which has a dipole going in this direction. In that case, the carbon that is attached to the electron withdrawing group will be reduced. Why would that be? It's because when you have that electron withdrawing group, it's going to stabilize your radical or your anion, and so that carbon would be reduced. All right, let's take a look at a couple of sample problems where we're doing a Birch reduction. So I have a few different compounds here. The first one, this compound, we call this cumene. It's isopropyl benzene, but the common name is cumene. And keep in mind that an alkyl group is an electron donating group. And so electron donating groups, that means this carbon is not going to undergo reduction. And so the product in this case is going to look like this, where we're going to maintain the double bond that's attached to our isopropyl group, and we're going to have our reduction like this. Remember, the two sp3 hybridized carbons have to be opposite to each other like this. Now, if you wrote it this way, if you wrote the product like this, so you had it look like this, keep in mind that these two compounds are identical to each other, okay? They're the exact same compound. All right, let's take a look at this one where we have a methyl group and an isopropyl group on it. Now, keep in mind that these are both electron donating groups. This is an electron donating group, and this is an electron donating group. And so neither this carbon nor this carbon is going to be reduced, and so the double bond is going to have to stay in that position. And so our final product will look something like this, where we have our methyl group here and our isopropyl group like that. The next one, keep in mind that a carboxyl group is an electron withdrawing group, and so that carbon is going to be reduced. And so the product we're going to get in this case, when I say that carbon, I mean the carbon that is attached to the carboxyl group. That carbon will be reduced. And so our final product is going to look like this. Here we go. And for the last one, we have a carboxyl group, which is an electron withdrawing group. So that means that this carbon will be reduced. And then we have an electron donating group here because it's an alkyl group. So this carbon will not be reduced. And so our final product will have to look, if I can squeeze it in here. So we're going to have our carboxyl like this. We're going to have our isopropyl over here. So that means we're going to reduce here. We're going to reduce this carbon and this carbon. And that's going to be our final product like that. And so there you go. It's a little bit of practice on the Birch reduction.